Hello, my name is Matthias Hertel. Thank you all for joining. Before we get started, let's look at the agenda of the next 30 minutes. I will start with a little overview of machine learning and CMSIS. Then NXP will introduce its latest MCU family, the i.MX RT, and we will learn about its unique advantages for modern embedded applications. Right afterwards, we will jump into action and I'll demonstrate a real-life use case of machine learning on the i.MX RT, the keyword spotting application. So let's look at machine learning in general first. Machine learning is the art of giving a computer the ability to learn without being explicitly programmed. At least this is what Wikipedia tells us about it. Typical use cases are the automatic recognition of speech or visual objects. The idea of a thinking machine exists since over 100 years, but just lately became an applied technology. Modern scientific findings like artificial neural networks and deep learning, combined with a large data network like the internet and affordable compute power and cloud-based clusters, mark the beginning of a real machine learning revolution. As machine learning is one of the most memory and compute-intensive tasks out there, you might now ask where this fits into the context of microcontrollers. This is what we will look into today and find out how ML comes down to the node and where Arm's technology leads the way. Before we explore how, let's look why machine learning tasks might be run on a microcontroller system. There are various reasons to operate these on the node rather than in the cloud. One is bandwidth constraints. In cases where the network access is limited, this is obvious. Another reason gets clearer when you look at the forecast of the IoT market. By 2021, IoT devices will outnumber all other internet-connected devices, like mobile phones and PCs. By 2035, there will be likely 1 trillion devices connected to the internet. Minimizing network traffic will be a key focus then, especially since there's a physical limit to communication bandwidth. Other reasons are latency, reliability, or security. Eliminating the communication layer lowers the response time of machine learning tasks, where a quick decision is required, and removes the risk of a network not being available or compromised. Let's look at the type of applications that are in reach of a Cortex-M based system. Typical use cases are keyword detection for a voice-based human-machine interface. Also, object detection using visual or other sensor data, like ultrasonic, is a common case that a Cortex-M processor can deal with. When looking at the popular software frameworks for machine learning, like TensorFlow, Caffe, Theano, and others, it becomes clear that these can impossibly be operated on even the largest microcontroller. The amount of resources and compute power required is magnitudes beyond what is available on an MCU system. To overcome this problem, a simple solution is to split the process into two fundamentally different tasks. The first is to train the model. This involves building and training a complex model that includes the intelligence for our task. This is a compute-intensive task, usually involving huge and pre-classified datasets, which are repeatedly run through the model so that it can improve its ability to, for example, classify images or recognize speech. The second is to use that model in the real world. This can be optimized to run on constrained devices like MCUs. While the learning process is resource-hungry and not real-time, the inference process is often real-time and low latency. It can be built to use the pre-trained model using optimized algorithms to produce just the right amount of accuracy to allow the system to respond in a safe and meaningful way to its environment. So you can see this is the first process, learning, that can be carried out offline in advance using pre-prepared data. The second process, the inference, is carried out at the edge independently of the network. And this is where the embedded bit comes in. The majority of devices in the embedded space today are built around Arm's Cortex-M processor cores. One of the latest members of the family of Cortex-M based MCUs is the i.MX RT by NXP. I'm happy to have NXP here to give us a quick introduction to what the i.MX RT is.
Hey, good morning, afternoon, and evening. This is Mario Centeno, one of the product marketers for i.MX RT. Thank you for joining this webinar. And before we jump into the details about the ARM neural network SDK and their CMSIS neural network, I'd like to share with you some insight into the RT series. So I'll spend a few minutes talking about that and then hand it back to the ARM team to go over their portion of the webinar and a demo. So what you see here is a slide that talks about our crossover processor, which is where the RT series resides. What we've done here is essentially taken the best of both worlds. We've taken characteristics that come from our i.MX portfolio, which is on the top left, and characteristics that come from our MCU portfolio, which are on the bottom right. And what we've done is created this new series within the i.MX portfolio. So this is the first Cortex-M7 in the portfolio. It runs at 600 megahertz, and it runs a complete a software environment that you're used to from our MCUs. So we run MCU Expresso, FreeRTOS, as well as IR and Kyle in terms of IDEs and tools. Let me jump into some of the highlights or characteristics of the RT1050, which is the first device in the series. You'll start hearing about other devices from us this year. We have a RT1020 that's coming in June, and the RT1060 that'll be in production in October of this year. The first device is the RT1050, and really what we wanted to do is focus on the Cortex-M7 and push the performance. So it runs at 600 megahertz. That's 50% faster than any other M7 in the market. We've also pushed the amount of SRAM that's on board, and in this case, the RT1050 has 512K of SRAM on board, and it can all be configured as on-chip SRAM or tightly coupled memory. And what you'll see is that is the highest in the market as well. In terms of high level of integration on the bottom left, we've brought over a lot of the characteristics that you're used to in our i.MX 6 product line. So we brought in encryption engines, high assurance boot, and on-the-fly decryption on the quad SPI. So when you're interfacing with external memories. We have a 2D graphics acceleration engine as well, and a parallel and LCD interface. On the right side, it was all about ease of use for customers. So we wanted to lower the BOM costs, and what we've done is we've aggressively priced the device. So if you go through any of our distributors, you can find the RT1050 starting at $298 for 10K units. We integrated a DC to DC on the device. And as well as in our 10x10 package, you'll see in our EVK that we've enabled a 4-layer PCB design as well. From a software perspective, we have a MCU Expresso IDE, but support from IR and Kyle as well. And our SDK is enabled with the FreeRTOS as well. Let me jump to the block diagram. So the device comes in one package today. It's a 196 BGA 10x10 0.65 millimeter pitch device. In August, you'll see that we'll bring a 0.8 millimeter pitch device to market. It's offered in 2 different temperature ranges, so consumer and industrial. And you'll see in the middle of the box some dotted boxes in there, and those are optional features that come in the device. So I'll show you when you go order the device. You can order devices with the multimedia enabled or disabled. One other thing I will highlight is there's no embedded flash on this device. So we have external memory interfaces, so you can interface to quad SPI through the dual channel quad SPI that has a bus encryption engine, as well as you can interface with SDRAM, NOR flash, and NAND flash with our external memory controller. Let me jump to the Orderable part numbers real quick and then show you the EVK and hand it back to the ARM team. So we have 4 different variants that are available. There's 2 industrial temp devices. So the 1052 and the 1051 are industrial temp devices running at 528 megahertz. The difference between the 52s and the 1051s is that the 1051s do not have any of the multimedia IP enabled. So there's no LCD or camera interface. or the PXP, which is a 2D graphics acceleration engine. The 1052s do have that enabled. So we offer the same combination, the 1052, the 1051 in the consumer temperature range, same package, and those devices run at 600 megahertz. Let me jump to the EVK here. So the EVK is available today. It sells for just under $80, so $79 resale through our distributors or nxp.com. There's an option to buy a separate display that's available for just under $30. With this EVK, you'll see that we are running the 1052 consumer temp at 600 megahertz on the EVK. The Gerber files and schematics are all available online, and you'll see that we've enabled a 4-layer PCB for this device. There's an Arduino connector as well that's on the device. There's a SDIO connector, Ethernet, as well as various audio inputs as well, in case you're interested in that, as well as the connectors for the display. With that, that's just a real brief summary of the RT1050, and then we want to spend the rest of the time talking about the ARM neural network and their SDK and the CMSIS and how to enable machine learning on your devices. Thank you.
Thank you very much, Mario. Now let's look at how a machine learning task can be implemented on an MCU like the i.MX RT. A key technology that enables ML in the deeply embedded space is called CMSIS-NN. First, let's look at CMSIS in general. If you ever did a development on a Cortex-M based microcontroller, you will likely know CMSIS already. If not, imagine CMSIS, the Cortex microcontroller software interface standard, as a collection of standards and software stacks required for consistent developer story across all Cortex-M MCUs. So what is CMSIS-NN? CMSIS-NN, as in neural networks, is the latest addition to CMSIS. CMSIS-NN is a software component that contains efficient kernels developed to maximize the performance and minimize the memory footprint of neural network applications on ARM Cortex-M processors targeted for intelligent IoT edge devices. It utilizes existing CMSIS components like the CMSIS DSP library and CMSIS core for simple and optimized deployment on all ARM-based microcontroller devices on the market. The library includes functions that implement popular neural network layer types, such as convolution, fully connected, pooling, and activation. These functions can be used by the application code to implement the neural network that was pre-trained on a machine learning framework. The kernel API is also kept simple so that it can be easily retargeted from any machine learning framework that you use to develop the model. ARM's machine learning components create a comprehensive story for the developer of neural network applications. First, you choose an NN framework that suits your requirements best, like TensorFlow or Caffe. If you gained experience with one of the common frameworks and created a workflow, you can just continue to use this. Arm NN bridges the gap between existing NN frameworks and the underlying IP. It enables efficient translation of existing neural network frameworks, allowing them to run efficiently without modification across ARM Cortex CPUs and Mali GPUs. Arm NN is free of charge, by the way. Arm NN can retarget the model to run most efficiently on the selected platform. In the case of a Cortex-M processor, like the i.MX RT, this will be CMSIS-NN. CMSIS-NN can achieve up to 5 times higher performance over a standard implementation using the specific features of a Cortex-M processor. Where do these improvements come from? Let's look at the keyword spotting example that we run in a minute and see how much performance CMSIS-NN gains on this and how it does this. The default implementation that will run on a model from an NN framework for audio data will typically use a 32-bit float data type for the input data. This is where the gain using the FPU offered by the processor already comes into play. There's some gain using the FPU, but the FPU does not always come with advantages only, as you have to stack larger stack segments on interrupt entry and other things. So fixed point math is the preferred choice of an embedded developer wherever feasible. In the case of the keyword spotting neural network, a 16-bit fixed point type from the CMSIS DSP library shows the best ratio of memory usage and performance, while still having the accuracy almost not impacted compared to the float type. CMSIS-NN provides specially optimized variants of the required functions underneath that add up to the overall performance improvement of 4.8 times faster than the standard implementation. The standard implementation of the keyword spotting neural network would actually require a Cortex-M processor with around 60 MHz, but this processor would be utilized 100% to run the network. Reducing that to a fifth means that you actually gain 80% CPU runtime for other tasks. If you now extrapolate that up to the i.MX RT that actually runs at 10 times the processor speed, you see that the neural network execution time actually gets a 1-digit percentage of your total CPU time, and it's just another side task that can just be easily run even next to a complex application. Now let us look at the CMSIS-NN in a real-life use case. Keyword spotting in the context of speech processing is the ability of the machine to detect a set of spoken commands, also referred to as keywords. The most popular occurrence of this technology is the wake keyword on popular audio assistants like from Google, Amazon, or Apple that are activated by saying, "Okay Google, Alexa, or Hello Siri." Let's get an understanding of the fundamental flow of our keyword spotting application. An acoustic signal is recording using a microphone connected to the audio duct on the i.MX RT evaluation board. The codec provides a stream of digital audio data converted to floating point values at the input stage to utilize the Cortex-M7 floating point unit in the audio pre-processing. One of the first things to do in an automatic speech recognition is the extraction of so-called features. Although feature extraction is one of the most important tasks in speech recognition, I will only briefly explain what happens here, as it is not directly related to the machine learning. First, the audio stream gets windowed, meaning that the continuous signal gets sliced into smaller frames. A feature extraction method called MFCC is used to convert the input into a vector that can be passed into our neural network. For simplification, you can imagine this as an algorithm with transformations and remapping frequencies to a preset spectrum that imitates the human ear, simply spoken. In our application, we will output these features in a graphical way on the LCD, and once the MFCC algorithm created input data, we can feed the neural network and output the prediction on the display as well. When you start to design a neural network, you will be facing one of the most difficult challenges right from the start. This is selecting the right neural network for the job. The range of Cortex-M-based platforms gives a rough frame to move inside when considering memory resources and performance grade. For simplicity, we consider 3 system sizes, with the small systems ranging from the low-end M0 up to a low-power, low-clock speed Cortex-M4 devices without FPU. Medium systems will represent the most common MCUs from the last 3 years, built around a Cortex-M7 running up to 200 or 300 MHz with a megabyte of flash ROM and roughly 250 kilobytes of RAM. With the i.MX RT, the MCU world expands to a new outer border of 600 MHz core clock speed and introducing the large-scale MCU systems in our representation here. So the first parameters used to select a model are the requirements of a network and the available system size. MCU targets, compared to server farms with GPUs, for example, always require compact models that can run with a limited amount of memory. A second parameter, of course, is the execution time of the network. Most applications will actually have low power or real-time constraints, so a model with a small number of operations is mandatory. Last but not least, of course, a couple of parameters tied to the model type need to be evaluated. The number of input features, the amount of and types of layers, and others are set by the type of task. Not every model performs with every task. Literature often helps to reduce the number of possible candidates unless the task is something that actually has never been done with a neural network so far and there is no studies available. In case of the keyword spotting, this boils down to 7 possible models we've chosen that we evaluated regarding their performance on the specific task of detecting word keywords out of a set of keywords. The following NN models have been tested for accuracy and have been tested with a known test set and evaluated for the resource consumption. The deep neural network, convolutional neural network, and the convolutional recurrent neural network, the normal and the basic variant of the long short-term memory, gated recurrent unit, shortly GRU, and finally the deep stochastic convolutional neural network. Values are sorted into the charts and show, for example, that the DS-CNN provide very good accuracy of around 95%, meaning only 1 out of 20 spoken keywords is not detected, already with a very small network, while blending the lowest memory consumption of all test candidates with a medium compute requirements. Only if you have only very little CPU time to spare, maybe in battery-powered environments or lowest latency environments, and a 10% lower accurate result is not an issue, the DN is an interesting option. In the actual demo run, you will need to select, we will select this network now. We run this on the DNN variant. Since we are limited in time and this webinar should only give you an overview fitting into 30 minutes, I will not actually discuss the real implementation in detail, but already start running the application now. I took a picture of the setup on my desk that I will use to run the demo to give you an idea what this looks like. It consists of a microphone connected to the i.MX RT1050 evaluation board. Although the board offers an onboard microphone, I use an external one as the LCD and the microphone are on opposite sides of the PCB. The board will be programmed and powered using the USB debug adapter on the board. The adapter is CMSIS compliant, so I can directly connect the debugger with the IDE from Kyle MDK. To display the results, I attached the optional LCD module to the board, which is also available from NXP. To make a live stream of the LCD content available so that you can see it in this webinar, I also mounted a smartphone camera on top on a stand so you can see the image once I run something on the board. The project itself is set up in Kyle MDK, as this provides a very good experience when working with CMSIS components like CMSIS-NN. Its advanced debugging facilities will also help to tune the NN applications. I already loaded the project in the IDE, will now switch to it and start the debugger to download it to the target board. What you see is the Microvision IDE. For more information on the embedded software development with Microvision and Kyle MDK, I recommend to visit kyle.com. You will find plenty of books, videos and tutorials alongside the download of the free MDK Lite edition. I just attached the board, as you have seen in the demo setup, to my PC. The build and support for the onboard CMSIS DAP adapter makes accessing the board really simple. We are ready to download the application onto the board, which I will do now. The debugger stopped the application at main and was waiting for instructions. I will show you the live image of the LCD display and start running. Then I will give the application some voice commands that will be processed by the neural network. The result will be displayed. Left, 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 off, 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 So as you can see, the detection rate is very good. We do have pretty ideal conditions here in the lab though, with only very little background noise. Let's have a detailed look at the output of the demo application on an enlarged photo of the display content I made before. On the top section of the display, a waveform representation of the input signal is drawn. This gives a visual feedback of the digital audio input to the MFCC algorithm. The middle section visualizes a series of MFCC coefficients, as I explained before, which are output from the pre-processing stage, and which then also is the input stage for the neural network. The bottom section displays finally the result of the classification of the neural network made. So the i.MX RT1050 we used is actually utilized only up to a single-digit percentage with this NN task, thanks to the ARM-specific optimizations of CMSIS-NN. So you can see that this can easily run alongside any complex software project you can realize on this platform. During this summer, we will continue to release material like papers and videos to explain in detail how to create and optimize CMSIS-NN applications. Make sure to sign up to the ARM newsletter if you don't want to miss any of these. I also prepared a list of useful resources if you want to start right away. Find information about the development tools on kyle.com/mdk5. More information on NXP's new and powerful platform we used here will be found on the second link. Your best spot for CMSIS-NN is the CMSIS-NN blog that also discusses today's application, and the GitHub repository of CMSIS, which contains the latest sources and documentation. There's also information on Arm NN, and last but not least, a very detailed scientific paper on the keyboard spotting application you have seen to dig into the theory right away and learn for your own projects. Let's recap the last 30 minutes. Machine learning is moving towards the edge. In the future, even small MCU systems will have the ability and requirement to run neural network tasks locally. While ARM became the key architecture in the embedded space in the last decade, it becomes clear that one, if not the most important technology to create an intelligent network of smallest devices will be the Cortex-M family of processors. With the keyword spotting application, we got the actual proof that it is not necessary to have a GPU cluster at hand to run a neural network. When choosing the right model of networking during the design phase and combine this choice with the optimized CMSIS-NN library, neural networks can be deployed literally everywhere.